Here's a quick summary, and this will lead into the theory versus reality discussion. So we've used matrices and vectors to understand systems of linear equation. And then one of the first results we got was that a system of linear equation will have a solution for every possible vector on the right-hand side if and only if the determinant of A was not equal to 0, okay? So we can actually add another statement to that, and it's sometimes fun to write the following are equivalent. The following are equivalent. All it means is that A, if and only if B, B, if and only if C. So each statement implies the other. Okay, so the first thing we had was determinant of A not equal to 0 being our magic condition for existence and uniqueness of solutions. And then what we were talking about on Wednesday is this magic matrix called the inverse. If it exists, by definition, it has to satisfy that it doesn't matter on which side of A you multiply by the inverse, you always get the n by n identity matrix. And then we talked about the definition usually says you should check both of them, but for real numbers, this one and this one implies the other. Okay, so that's what the TFAE, the following are equivalent. Okay, so here's this nice property that we check, and then we can get the matrix inverse. And then we saw that the matrix inverse was nice because we could always write down X equals A inverse times B as the solution of the equation. So that's super convenient to be able to write that down. So why would we not want to use that all the time? That's the question here. Okay, so today, the theory versus practice gap. And then we'll move on to doing the more abstract side of linear algebra. And that'll give us the tool to study the existence of solutions when we don't have A being invertible and things like that. So we need it, the more abstract stuff, but that's what we're going to do. So here's the first thing. So let's look at A inverse times A equals the identity, okay? So let's just write that, what that looks like. Okay, and then that's supposed to equal A times A inverse. So this is the n by n identity matrix. Okay, the columns of the identity matrix all look like this. E sub I is 0, dot, dot, dot. I'm really bad at the dots. 0. You have a 1, another 0, dot, 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 0. And that 1 is in the ith entry. Okay, so E sub I is, so this would be E1, this would be E2, this would be En. So we just use the columns of the identity matrix to define these really special vectors. So I'm going to give you a fact and then an exercise to play around with in Julia to understand it. But here's the fact. Computing the inverse matrix is the same thing as solving the linear equation AX equals E sub I for I equals 1, 2, dot, 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 up to N. Ooh. Okay, so is there a point? Well, typically, we're trying to solve the equation ax equals b, and it's very pretty to write it down as x equals a inverse times b. All we're trying to do is solve one set of linear equations. I'm going to have you do some stuff in Julia to understand that when you cheat and go x equals a inverse times b, for little problems you just don't care, but when you start getting these big matrices, 1,000 by 1,000 and stuff, then it's equivalent to solving 1,000 sets of linear equations. And that's not going to be very fast, right? So that's one of the problems to do it. So all I want you to do is an exercise. So you can just do it with a random matrix. So here's my random matrix. I hope that's invertible. You think it is? Good chance, right? So just take this and then solve a times x equals ei for I equals 1, 2, and 3. And then place the solutions as the columns of another matrix. And we'll just call it B. So this will be solution 1. Let's see if I can squeeze that in. Solution 2, solution 3. And then just check that A times B equals B times A equals the identity 3 by 3, okay? So my colleague and very good friend, Chad Jenkins, who helped me found this course, likes to say, coding is believing, okay? So just code it up. It'll take you 5 minutes, right, in Julia. Open up, hit the little plus, get a little line there, do A equals random 3 by 3 even, and then just solve the equations. And you can use LU, you can use whatever you want, okay? You can just cheat and say x equals A inverse times B. I don't care, just get the solutions, but then stack them up, and then you'll understand what's going on behind the scenes when A inverse is being computed. And you realize that when n is large, doing this 1,000 times is an extremely inefficient way to compute one solution when that's all you want, okay? So that's my point. You're really solving the same problem over and over and over and over again with just very special vectors, and you just wanted that one solution. Okay, so that's the first part of the theory-practice gap, okay? So A inverse is computationally intensive. And is a very inefficient means to solve AX equals B. So 99.9% of the time in a course when you're computing an inverse matrix, it's always to get X. And you just take the inverse matrix, you multiply it times B, and for little bitty problems, even up to 30 sometimes, it just sort of doesn't matter with modern computers, okay? But if you're doing heavy-duty computations in real life and an internship this coming summer, hopefully those start opening up, then you'll find out that you don't want to do that over and over. So that's aspect one. Okay, so aspect one. Here's the next theory versus practice gap. Okay, here's the theory. Determinant of A not equals to 0 if and only if A inverse exists. Okay, so when you have a condition that it only fails for one number, okay? One number. So take a matrix for which that determinant is 0. Now just choose any number at random and just change one of the coefficients or something. Chances are it's now going to be not 0, okay? It's a really strong condition to have all of those products and everything you need in the determinant to be 0, okay? So anything equal to a specific number is kind of fragile from a numerical point of view. So what I want to convince you of is that in practice, even determinant of A fairly far from 0 can be misleading. Determinant of A is an unreliable friend, okay? This is the way to keep it in your mind. So, what could Grizzle possibly mean by the determinant is an unreliable friend? I mean, this is a beautiful condition, theoretically, spotlessly true, and everything. Okay, so question, what is the determinant of the n by n identity matrix? It's 1. It's lower triangular, it's upper triangular, you just multiply the elements on the diagonals. That's 1. Okay? What would be the inverse of the identity matrix? What should you multiply by the identity so that you get the identity? Another identity matrix, okay? So it's self-inverse. So the inverse of the identity matrix is an identity matrix, so it's a simple, very simple inverse, okay? Okay, so let me introduce, whoops, wrong place here, an example and show you that even determinants that are around 1 can give you some really bad information. Whoops, images. I want example 2, part A. Bingo. Okay, so this is in the book. You don't need to copy it down. It's example 2 in chapter 6. Okay, can we see this matrix? So this, whoops, come on, stay put. So we've got 100 here, 100, 95. I mean, the numbers are all kind of reasonable, nothing spectacular, okay? Its determinant is 0.9, so that's pretty close to 1, okay? So if you get 90% of what you're after, I mean, you're pretty happy usually, so it's really close to 1. Now look at A inverse, 10,800, 11,000, 10,000, 111, okay. Whoops. Now question, whoops, that's going to go away. Question, How do you often obtain big numbers from, let's say, medium numbers, okay? Kind of a rhetorical question, because nobody's going to be brave enough to put out a guess. But you know, it's typically you divide by small numbers. And I'll just call them tiny. Okay, so that's a really good way to generate big numbers. Divide by 10 to the minus 5. Yep, that'll generate a big number usually, okay? So if I'm computing this inverse, here's my big numbers. Where's the small number here that's going to give me 10,000? You can't see it, okay? It's completely hidden. And the determinant told me nothing. See? This is why I mean it's your unreliable friend. It's perfectly honest. The determinant is 0.9. The matrix is invertible. Okay. Do we have something else? Whoops, keep going to the wrong spot. Example part 2b. Now this is cool. We do the LU factorization. So that matrix I give you, is L times U. Here's L, we chose L to have 1 on the diagonals. We could have put the 1s on the U, on the upper part. It's a choice. But here, we're doing back substitution. The first thing is whatever the B is or etc., we're going to divide by 9. No big deal. But in the next step, look what we're dividing by. There's our small number, okay? It's now super apparent. You see the power of LU, not just as one of solving it, but also giving you information about how badly your equations are kind of numerically organized. We say conditioned, okay? So this uncovers the small number that explains where these 10,000s are coming from, even though the determinant told you nothing. So LU is a reliable friend, okay? It's telling you what's going on. So that's all I want to say on the theory versus practice gap. Theory, determinant of A not equal to 0, A inverse exists. Everybody wants you to know that in your future courses and your future life. You deep down know, well, it's a little nuanced, okay? That's all I'm trying to get. It's nuanced. Anybody like to follow up to get a little more nuance or to confirm that? Seem cool?
Yeah, sure.
Okay. Then we're done with inverses, determinants, transposes, and we start theoretical linear algebra. I'll ask again, anybody want to ask any questions about the nuances? No? Ready to move on? Okay. So now we're going to move on to theoretical linear algebra. Okay, whoops, I need this again. Insert. Where'd the file go this time? Image, file, thank you. Bingo. And I want the objectives for chapter 7. Okay, and I know you don't like to lay across pages. There we go. Okay, so where are we at this point? You guys know more about solving AX equals B than 99.999% of the people on the planet. and more than 99% of the people at the University of Michigan, okay? So solving AX equals B, you guys have a lot of tools and you know how to apply them. You're not afraid of big equations. You can program up the ideas and you can solve them, okay? So you know a lot about AX equals B, and that helped us understand the power of understanding this thing called a vector where we stack things up, a matrix where we stack up even more things, and things like that, okay? So it got us used to the vector matrix way of thinking. So what we're going to really start doing now is looking at collections of vectors. So the set of all n vectors, and then operating on those vectors and looking at properties of them. And these will then give us more insights into what's going on really when we have AX equals B. And when A has the property that it's nicely invertible, and when it doesn't have the property that it's nicely invertible. We'll start understanding how the columns of A interact in order to give us the property that our solutions have good numerical properties. Let's just say it in a way like that. And so we'll really be able to understand existence and uniqueness of solutions, and we won't be relying only on the determinant being non-zero to give us a special case. We're still confused when determinant of A is equal to 0. Do we have no solutions? Do we have an infinite number of solutions? We have no idea. And this theoretical development will uncover the answer to that. And then we'll start seeing, once again, how the LU factorization makes these theoretical concepts straightforward to evaluate in practice on real examples, where it's not the toy 2x2, 3x3 type things. So that's our goal. It's pretty awesome, actually. Questions? Excited for the new turning a chapter? Getting your theoretical caps on? Maybe. Okay. So we'll start out with some definitions, and we'll keep building on them. Then you can go away, because I don't need you anymore. Okay, so definition. Okay, an n-tuple. You guys kind of know what this is because you've been playing with Julia. Programming is believing. So it's just an ordered list. For us, numbers. Whoops. It's an ordered list of n numbers, okay? Not n plus 1 or something like that. And I'll write the traditional way, x1, x2, x2, very good. It's an ordered list, dot, 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 xn, okay? Whoops. So in Julia, it is any one-dimensional array. Okay, so n-tuple, this ordered list, and it corresponds to an array. Now, if we just have n numbers in an array, we can either put them in a column or we can put them in a row, okay? So this is where we're headed, okay? So and just to get our notation super clear, we use the symbol R to denote the real numbers. So for us, R is the same thing as the infinite interval minus infinity to infinity. It does not include minus infinity and plus infinity. So recall that infinity is not a number. Number, not mumber, number. It's a concept, okay? What's the deal with my N's and M's today? It's a concept. Okay, so infinity is that symbol such that it is greater than any real number, okay? So, but it's not a number. Definition, Rn is the collection of n tuples. Okay, so each of the elements is a real number, and I is between 1 and n. Okay, so it's all n tuples of real numbers. That's Rn. Okay, so it's a set. It's a collection of n tuples. That's what we call Rn. Now here's the cool thing that we do in mathematics is we identify, and that's a confusing word at first, and we'll talk more about it, but we identify Rn with the set of column vectors of length n. Okay? I think in this course we're now much more comfortable with thinking about vectors as stacking them up into columns. We're super comfortable with that. So what does this identify mean? It means this, that even though Rn is, try to write it more compactly here, okay, and I'll leave out I equals 1 to n. It's basically assumed, okay? So there's n of those guys. We say that this is the same thing, and I'll draw my curly brackets in a second, as x1, x2, dot, dot, xn, such that the xi's are in R. So what does the word identify mean here? That means if you give me a list of n numbers ordered, I will stack them up into a column vector. And if you give me the column vector, I can extract the n elements and put them in the same order here. So it's really the same object, just written in a different way, okay? That's all it is. That's all it is. Okay, so R to power n is column vectors of length n. So for us, and most of the planet, element of the set Rn means simply x is a column vector. Okay? Keep saying the same thing over and over until it becomes believable, okay? That's how our politics works today. That's how we're going to do math today. Say it over and over. Elements of Rn are column vectors. Now on, the column is assumed. We're just going to simply call them vectors. Okay? So Rn is the collection of vectors, all the possible vectors you can build out of the real numbers by stacking them up into columns. Okay? That seem too hard so far? No, it seems totally tedious, and he's beating it into the ground again, okay? So just as a remark, we could have chosen to identify with rows. It's just a choice. Okay, so there are applications where that's a good thing to do. We're going to do vectors, and the reason we're using vectors is the same thing as when you're driving. It's good that you drive on the same side of the road as everybody else is doing, okay? No matter what that is, and most people are using Rn as column vectors. So that's what we're going to start with. It's just an arbitrary choice, okay? It's completely arbitrary. Good. Now, what's the first consequence of our choice? So if A is an n by m matrix, then its columns are vectors in Rn. Okay, so we just take the matrix, we extract its columns, we have built elements of Rn. We can manipulate them with some rules that we'll develop. Conversely, given a finite set of vectors, in Rn, we can stack. We put them in sideways, okay? We don't really stack them up and down, but we stack them in sideways. We can stack them together and form a matrix. A equals n by m, that is a set of m vectors in Rn. And I'll write it out more explicitly. But the key thing is it's not an infinite thing. We don't have matrices that are n by infinity. We don't know how to put those into Julia. Okay, so it's a finite set of vectors. Matrices and finite sets of vectors, they're exactly the same thing. Okay, so if we do A and it's A11, A21, AN1, let's see, A12, A22, AN2 dot dot dot, A1M, A2M, ANM. We can write that as A column 1, A column 2, A column M, and if we just look at the jth column, first row, second row, nth row, those are elements of Rn. So let me let you catch up with your note writing there. Really all we're doing is vocabulary here, and you know how exciting it is when you're learning a new language and you're doing vocabulary. The next most exciting thing is verb conjugation, and then you do all the adjective agreements. Okay, we're not getting to that, okay, but vocabulary, that's usually not so fun, but okay, matrix, there's a vector, there's a vector, there's a vector. Sometimes we just use a single symbol for the vectors, but they all have n elements because they're in Rn. It's because it's an n by m matrix. And if you give me just 17 vectors that have all the same number of components, I can just stack them up and build the matrix. So matrix, finite set of vectors, matrices. They're the same thing as long as the vectors all have the same length, okay? I can't take one of length 3 and another one of length 7 and put them together and build a matrix. All the columns need to have the same length, okay, size. Okay. Here's going to be another thing that's totally transparent to you guys. Two vectors, x and y, in Rn are equal if and only if xi equals y sub I for 1 less than I less than n. So two vectors are equal if and only if they have the same components. x1, x2 equals y1, y2. Yeah, it's more obvious if we write it out. If and only if x1 equals y1, x2 equals y2, xn equals yn. Cool. Well, once we have that, we can define vector addition. Okay. If I have x1, x2, xn, and I want to do their sum, well, you guys have been doing that forever now in Julia and even in homework indirectly. The sum of the vectors is just the sum of the components, okay? So that's how we do it. We know how to do addition for real numbers. Okay. This almost seems pedantic, okay, but you guys know what this symbol means here for addition of 3 and 7 to get 10. We've just defined what it means now to add 2 vectors. Now we're using the same symbol here and here. Does that bother you? You're okay with that? Good. Because otherwise, then when we added if we start adding matrices, which you guys have done, when LU we're adding and subtracting matrices all the time, imagine you needed a different symbol for the matrix addition. And then when you have 2 functions and you're adding them and you need a different symbol for adding 2 functions, it would just drive you crazy, right? So what we do is we overload, okay, we overload the addition operation, and context has to keep it clear. That's what we're doing formally, okay? Good. And then we define scalar times vector multiplication by, if A is a real number, and we have x1, x2, xn, let me just call that x, in Rn, then A times x is by definition, whoops, I should have put over here. That's a definition because I was defining what the symbol addition means. This is A times x1, x2, xn, and this is defined to be A times x1, A times x2, dot, 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 A times xn. Okay, no surprise. Okay, only surprise, why is Grizzle wasting our time on this, okay? That's the only surprise. Okay, so what we're doing is defining the rules of operation on this set. The set of n tuples, which we identify with column vectors, we're defining what it means to do algebra in this set. We can add elements in the set. We can't multiply 2 elements in the set, but we can take a real number and multiply it by an element in the set and get another element in the set. Okay, so if we add any 2 vectors, we get another vector in the set. So that sometimes one says the set is closed under vector addition. I do addition, I don't get something that's outside of it. It stays in it. Formally, you say it's closed under vector addition. And it's also closed under scalar times vector multiplication. I take a scalar, I take a vector, I multiply them, I get another set, I get another n vector. Okay, we're going to end with another part that is kind of just recalling things, and you guys have to tell me when in high school I learned this, okay? 6th grade, 8th grade? A plus B equals B plus A. A times B equals B times A. Those were called commutative properties. Don't worry, we don't care, okay? They're just setting us up for the corresponding thing on vectors. Let's see. if we add A plus B first and we add C, that's the same thing as adding A to the sum of B and C. And if we multiply A and B first and then multiply by C, that's the same thing as if we multiplied B and C first and then multiplied by A. Associative. Final one. If you take A and you have the sum of B and C, that's the same thing as A times B plus A times C. Distributive property. So when did we learn that kind of stuff? 8th grade? It's hard to remember for me, okay? What about, I thought you guys would remember. Tribby, do you remember? Okay, you were trained in India. You probably taught that in kindergarten, okay? So that's how things work there, okay? So we have similar properties for vectors. It's the only thing I want to point out, and then we stop, basically. Okay. If I have a vector, let U, V, W be in Rn. Sorry about that. Should have written that down. If I first add U and V and then add W to it, I get the same thing as if I add V and W first and then I add U to it. Okay, seems obvious, but why is it true? We don't do proofs in Rob 101, but why is that true? It's because we define vector addition component-wise. So it's true for each of the components, and then it's true for the vector. Okay, so this is the theoretical part. We take things for real numbers, those properties, and we lift them to this more complicated set. That's all we're doing, okay? Why is it true? It's because of the way we define vector addition. Okay, now let's let A be in R. If I do A times U plus V, that's equal to A times U plus A times V. Why is that true? Because of the way we define scalar times vector multiplication, component-wise. Because it's true for each component, because they're just real numbers, it's true for the vector. Okay, so that's the thing. And then if B is also a real number, and I multiply it times U, so I need to say B in R, you should get A times U plus B times U. Okay, so those simple properties continue, and we'll stop here. And Monday we'll pick up with linear combinations, linear independence, all of the really cool stuff about abstract linear algebra that will lead us to understand the columns of a matrix, and then will lead us to understanding existence and uniqueness of solutions for cases where the A is not even square. So that's the point. We'll understand for A not even square. Okay, thank you, everyone.